Hello, everyone. Today we are going to talk about some more advanced topics about modular arithmetic, and basically we are going to talk about something about solving equations. Um, because we know that we in solving when we are solving equations in algebra, we invent some number system, right? We have real numbers, which is when we are solving px equal to q, where p and q is integers, and we have irrational number, and it becomes real number. And when we are dealing with irrational numbers, for example, we are solving x squared is equal to 2, and we invent a rational number. And we have complex number when we are solving x squared is equal to -1, right? And we get x equals to plus minus I. And in modular arithmetic, we have something very similar. Let's talk about the first one. We If we encounter a modular arithmetic that, for example, px is congruent to q mod r, for example, what can we do about this? If Yeah, we've talked about this many times, which is to find, like this. We typically add the reciprocal of p, right? Similarly, we know that every p has an inverse here, so we also take the inverse, and we solve this equation, which is x is congruent to q times p's inverse. And we've talked about inverse many times, so we know we are not going to talk about it further. And let's see the second one, which is when we are talking about quadratic functions. And here it's called quadratic residues. Um, what do we mean by residues? Remainders, right? So we are generally talking about the equation which is x squared is congruent to a, and here mod p. We know we have some feeling when we are solving some problems involving squares. We typically when we for example we sometimes consider mod 4, because x squared can only remain 1 or 0 mod 4, right? And x squared can only remain 1 0 0 1 4 mod 8, right? And x squared can only congruent to 0 1 mod 3, right? Here we get some sense. We find out that there isn't all a. I mean, if we are given an equation x squared is equal to 2 mod 4, we don't have a solution here. It means that there is some constraints on a. The a There is some constraints. A only exists in some circumstance. So we define there's a definition. It's the quadratic residue. We mean we generally formalize our observation. We call A is a quadratic residue if there exists an x such that x squared is equal to a mod p. Essentially, we are saying that a is in the set that x have a solution. Yes, and we are going to talk about this in detail further in next lecture. And here we just skip it a little bit, and we can talk about something that invents complex number. And let's talk about complex number in the sense of modular arithmetic. So how about complex number? We are solving equation like this, right? What this is complex number in modular arithmetic, and we can have some feeling about it. We want to check the set x squared plus 1, and we want to see if we can find a, that is, there exists some, let's write it as a squared plus 1. We want to find out that if there exists any a such that this is divisible by such as p divides a squared plus 1, right? And this is quite, we can first experiment, right? Experiment is very powerful. So this is p, and we can start with for example, p is equal to 3. We know that we what we only need to examine is 0, 1, 2, because if 3 is congruent to 3 square is congruent to 0 square, and 4 square is congruent to 1 square, and we don't need to consider those. But at the same time, we don't need to consider 0, because 0 squared plus 1 is always 1, and it's not minus 1. And we also don't need to consider 2, because 2 is congruent to -1, and -1 plus 1 is always congruent to 2. And it's never except 3. But in other cases, it is not congruent to -1. But here, when p is equal to 3, we see that there exists the 2 is a valid solution here. And when p is equal to 4, 0 we need not to consider. 1 we also don't need to consider 1, because 1 square is congruent to 1. And 2 we don't need to consider, the 2 isn't a valid solution. And 3 isn't 3 square is 9, and we don't need to consider 4, because 4 isn't a prime, right? We consider 5, and 5 1 0 1 4 9 16, right? We know 16, we know 9 is what we are talking about, and 16, we don't need to consider the two extremes. We don't need to consider 1, and 4 is also the correct answer. So we find sometimes is all the a comes with in pairs. That's a observation we find out, and indeed, because we know that this square can kind of make the negative and positive seem alike. Therefore, we have, if a is the valid solution, it implies p minus a is also a valid solution. And we've talked about a lot, and let's talk about a very important theorem in modular complex number, which is called Fermat's Christmas theorem. This is p is a prime, and the theorem implies that the condition where there exists an a such that a squared plus 1 is divisible by p is there's a condition with p to exist an a. The condition is let's write it out. When p divides x squared plus 1, we if and only if p is congruent to 1 mod 4. And think about this. We know that oh sorry, it isn't. It's 3. There does not exist a, a residue here for p equals 3, but it indeed exists for p equals 5. Therefore, we see we can if you test more, you will find it doesn't exist for p equals 7, but it doesn't exist for p equals 11, but it exists for p equals 13. And it's reasonable to conclude this statement, and we will prove it in the next video. Thank you.